Swayamprabha. Digital India. Educated India.
Welcome back. Towards the end of last class, we had completed our discussion of some mechanical measurement techniques that are applicable to measuring external spray characteristics. We will spend some time today talking about non-intrusive measurement techniques to measure both external spray characteristics, both macroscopic and microscopic. Okay. So, we will learn a little bit about non-intrusive measurement techniques. So, we will take the simple example of videography first. We will see what a videography, which includes photography, what does it tell us and what does it not tell us. So, if we go we are going to start by playing a very short video. As you can see, this is a classic perfume spray. I am going to pause the video here. The classic perfume spray that tells us a little bit about the nature of the spray coming out of a standard perfume bottle. You can see that there are drops far downstream, you can actually see the drops, but close to the spray nozzle itself you really do not see individual drops, but again close to the spray nozzle you can discern, you can understand the idea of a spray angle. So, macroscopic measurements such as spray angle and maybe even spray pattern can be understood from a simple videograph like this, or a photograph, or even an individual photograph. We will play this for a short while. Not only that, as you can see right now, this is a case of a steady spray. In other words, I had the perfume plunger depressed, and that caused a steady squirt of perfume coming out of the nozzle, at least seemingly steady to my naked eye as I was spraying, but this video is a high speed video taken at about 3600 frames per second. So, at that resolution, at that time resolution, you can see that there are structures. As you can look at this little white patch, I am going to show, you can see that the white patch diffuses further downstream and there is another white patch that forms. So, it is not like a continuous spray, it looks like there is some semblance of unsteadiness. Another example is right here. You can see that there is a little inverted V like structure with the tip of the V pointing away from the nozzle. These are classical so called inverted chevron structures that you will see in most sprays, and we will come back to look at the origin of one of these structures later on. But the point to note here is that in a simple video we are able to make some sense of a lot of these parameters. Now, what other information can I get? Let us talk about spray pattern for a moment. Now, this spray presumably is axisymmetric. So, what I am seeing is just the peripheral outside of the spray. So, if I have an axisymmetric spray, I am going to see in a video or a photograph, I am only going to see the outside, not really going to be able to see much of the inside part of the spray. So, if I want to see the inside part of the spray, if I want to sort of take a cross sectional view of this spray, which is what an inline patternator does. If I want to take, or if I want to take a cross sectional, if this is my nozzle back here and if this is a spray, if I want to take a cross sectional view in this sense and look at uniformity just like a sector patternator would do, I still need to figure out a way to make a cross section. And that is where this kind of illumination, where essentially this is like a set of lamps surrounding this spray that were used to illuminate this particular spray. This is not particularly useful if you were to do that. So, let us make some notes on what works and what does not work. So, one could make spray angle measurements. One could look at unsteadiness in the spray. And you could also look at pattern if there was a way to take a cross sectional view. So, how do I take a cross sectional view? By looking at the so called plane illumination. So, I can take a, let us say, a torch light that puts out a cylindrical beam of light of some diameter d. And by a set of lenses create a height h of, create a light sheet that is of a height, some height h, and the thickness would still be equal to the diameter of the beam. But if I start with a beam that is of a very small diameter, I can create essentially what looks like a rectangular sheet, a sheet of light that is of rectangular cross section. Now, if I use this kind of an illumination in a spray, I am only going to see the drops that are resident inside the spray. So, if my camera in this particular view is normal to the sheet where our eyes are located currently, then we would only see the drops as they propagate through this sheet of light. So, this plane illumination or light sheet illumination is a very nice technique to look at what is happening in a cross section. Now, I could also illuminate, I can have the spray be where my eye is, in which case I can create. So, if I have the spray nozzle where my eye is, I will essentially create a cross sectional view either this way, either a meridional cross section or an axial cross section, both are possible. The only problem with this kind of an approach really is that the brightness of the light sheet is quite limited, because you are unable to pack the brightness of the light sheet becomes a limiting factor. Therefore, most of these techniques, while they were feasible, were not really practical until the advent of the laser. The laser provided for a very nice way to pack a lot of energy into a beam. So, fundamentally what is different between a laser that puts out a cylindrical beam, let us say a 1 mm diameter beam, and a torchlight that also presumably puts out a 1 mm diameter beam. Okay. So, let us quickly make some differences. I will call normal collimated light. Collimated is where the light rays are all parallel. So, the first thing is laser is monochromatic. Typically lasers are monochromatic, that is all the photons that make up the light are of the same wavelength, unlike say normal white light illumination. Now, you could also get monochromatic torch lights, so to say, that are of a very narrow wavelength spread. So, you can essentially have a monochromatic light source, but the biggest difference between a laser and a normal light sheet, normal light source, is this idea of coherence. The fact that all the light that is being produced by the laser, all the photons are in phase. That is, if you imagine, the simplest way to imagine this is to look at light as an electromagnetic wave, that essentially if I have a light beam, if I know the phase at one end of the beam, I know the phase at every other point because they are perfectly correlated. This is not true with normal monochromatic light. So, if this is a laser, the wave that makes up this, the electromagnetic wave that makes up this light is essentially entirely coherent in phase, because of which all of the photons that are produced are only adding to your light intensity. There is no destructive interference causing resulting in loss of light intensity, and therefore, laser is a very nice source of illumination for photography and videography applied to sprays. So, if I create a light sheet just like I showed before, if this is now not a torch light, but a laser, I can create a beam of diameter d. Now, typically the divergence of this beam is usually very small, but it is not non-zero. It is most laser beams do have a small but positive divergence, fractions of milliradian usually, but the advantage is that it is a coherent beam. So, you can do a lot with coherent beams that you cannot do with incoherent light sources. Another feature of lasers is that it will always have a Gaussian distribution of intensity. The beam itself has is brighter in the middle than in the edges. So, this is So, if I take a laser that has a Gaussian distribution of intensity and pass it through a pair of concave and convex lenses just like shown there, that intensity distribution is still retained. So, the laser itself when distributed into a sheet would still be brighter in the middle here than at the edges. Okay. So, now let us go back to our video and look at how this can be of use to us. If I start off from some point over there, you can see that there are these white specks at this point where at the instance where I have paused the video, you can see that there are these white specks. Okay, now, those are presumably large drops that in this magnification look like white specks. Now, if I take another frame just a short instant later, I can look at those same white specks that have moved a distance downstream. So, by knowing the distance that these specks have travelled and the time spacing between the two frames that I just used to illustrate this point, I can extract a velocity vector. However, the only problem with doing it in a video like this is that I do not know if they were all moving in a plane or they may have moved towards me and away from me. So, when I do it with just diffuse illumination like I have used to make this video, I do not know the direction in which they have moved. But instead, if I had a plane light sheet illuminating the spray, then if the speck was visible in two successive frames, that means it was inside that plane only. So, that becomes a precondition to extracting the velocity vectors, without which you do not know which way they moved, and so you are somehow you are getting a component of velocity, but we do not necessarily know the exact plane in which they moved, especially because with the lens that I had to make this video, the depth of focus was fairly large. I do need that, otherwise most of the spray would look just blurred and a very small part of the edge of the spray would look like it is in focus, and that is not a very useful video to have. So, if I want to illustrate the points, so the macroscopic measurement variables, I do need a fairly high depth of focus on my video, but if I do that I do not know which way the drops are moved. So, the solution to this is use a light sheet, a plain light sheet, illumination plus let us say a high speed, or I put high speed in parentheses, but a high speed is not necessary, but what is necessary is double pulse camera. That is, I need a way to take two successive snapshots apart in time, they are such that I know the time spacing between the two snapshots. Okay. So, if I did that and if I went back a short distance, you can see these white specks right let us some distance from the nozzle. A short instance later all the white specks have moved, and presumably if this was a plane illumination, then all of the distance moved by the specks are in the same plane as the illuminated as the illumination sheet itself, and from knowing these two frames and the distance travelled, we are able to extract velocity, and this is called particle tracking velocimetry. This is the simplest of drop velocity measurement techniques. Where you follow individual particles and record the displacement vector over a fixed interval of time. So, let us say I have a spray that I have used plane illumination. So, this is my light sheet. And my camera is where my eye is currently located. So, in one frame, let us say a drop was situated over here. In the next frame, if this is the position of the drop, what I do know is that this is the displacement vector. The velocity is given by the displacement vector divided by delta t, the time spacing between these two, between the two successive frames. Only problem with this is that when I take a video or an image, like for example, we will go back to the one we just from looking at this video, if you did not know what a normal perfume bottle would look like, do you have a way of extracting how big this spray is? Let us see, let us take a simple example. Let us say I take this frame, I can see the white specks close to the nozzle, I move a short distance, a short time later I know the position, the new position of the specks. What I need is distance in millimeters or meters, some length unit. A picture like this does not really convey length units. All I know is displacement in pixels, because the camera works in pixels and in 3D voxels. So, when you have pixels, all I know is the displacement in the x direction in pixel units, displacement in the y direction in pixel units. So, I have to a priori, before I do this experiment, have a way of figuring out what the how many pixels corresponds to a length unit. So, that is called magnification calibration. So, I need to calibrate this system for its magnification. So, delta S in pixels times magnification in millimeters per pixel So, m is the magnification. In fact, typically given in units of pixels per millimeter, but we can also obviously invert this and get a length per pixel. This is required before one can extract quantitative length based velocity information, otherwise all I know is some pixels per second. Now, how would we do this? We typically use a feature that is of a known length, like in this case, let us say I know some distance here, let us like the plunger diameter or a height, a feature on a bottle like this, that is known beforehand, and by counting the number of pixels that make up that feature, we are able to extract the pixels per millimeter. Now, a lot depends on the kind of lens that is used in these kinds of photography and videography. There are a class of lenses that where the magnification is relatively uniform all around the image. So, if I do this kind of a pixel per millimeter calibration in one of the corners of the image versus the middle of the image, I will get a pixel per millimeter that is relatively the same, but I could there are other lenses which are. So, as I go smaller on the focal length of the lens, typically the magnification varies across the image. So, you are always better off with a very narrow angle of view lens, where the magnification across the frame is relatively speaking constant. Okay, now, if you are otherwise constrained to use a lens that has a very short focal length, then you have to have a pixel per millimeter measurement at different points in the image and use the actual pixel per millimeter at that location to extract the velocity measurement. So, in any case, I do need this magnification in pixel per mm to convert displacement in pixels to velocity in length units, let us say mm per second. So, this is the simplest of microscopic parameter measurements. So, let us say if I want to measure droplet velocity, all I have to do is create a sheet of light and look at the displacement of the pixel in the plane of the light sheet, and that gives me the velocity vector in the plane of the light sheet. If the drop was moving perpendicular to the plane, if it had a velocity perpendicular to the plane, I would not be able to measure that velocity component from this kind of a measurement. Okay. Now, if the drop did have a velocity component perpendicular to the light sheet, there is another thing that could happen, that I could see the drop in the first frame and actually not see the drop in the second frame, it just disappeared. So, I would not be able to measure the displacement of that drop. So, if I have to measure the displacement, it has to be present in both the individual frames that are some time apart for me to be able to extract velocity vector information. So, this is the simplest of droplet velocity measurement techniques. We will extend this. Now, the only problem with this is this, that if you look at what is happening like very close to the nozzle, I just have a little grayscale image. So, if you look at this particular region here, I can see these specks of white light, or down here I can see the specks of white light, but for the most part of the spray close to the nozzle especially, I do not see individual drops. I see like a smeared image where I am able to make sense of a group of drops. Like for example, if you take a region down here, I see that there are drops, but it is not where I am able to clearly follow one bright speck and look at displacement of a speck. So, in other words, if I focus my attention down in a small rectangle where I am pointing right now and look at an image now which is frozen, and a short time later, I cannot follow individual drops. They all look alike in this image. I cannot follow individual drops. This is going to be the case in most of the spray, except in the very periphery of the spray where I see flying drops, or except in the middle of the spray where I see bright specks occasionally coming out. These are large drops that I can mark. Except when that happens, most of the spray is going to look like a grayscale image with little dots, and I need to get velocity information from that. In order to do that, we have to move to an algorithm, to a technique called particle imaging velocimetry. The hardware part of